Good morning to everyone. I am Sadish Kumar from EC department in MEM School of Engineering. And now I am going to explain some important points for VLSI design. The outline of VLSI design, the first one is the scaling. The scaling based on transistors, interconnect, future challenges, and VLSI economics. The first one is the design was based on the Moore's law. In 1965, Gordon Moore predicted the exponential growth of the number of transistors on an IC. The transistors count doubled every year since invention. Predicted greater than 65,000 transistors by 1975. Growth limited by power. And the Moore law, and the transistor counts have doubled every 26 months for the past 3 decades. It is the basic diagram of the transistor 3 decades. It is the depending upon year and transistors. And the first of all, in 1917, 1000 transistors are used. In 1975, the 10,000 transistors are used. In 1980, 1 lakh transistors are used. In 1985, that 10 lakh transistors are used. In 1995, and the 1 million transistors are used. The 2000 the 1 billion transistors are used. The speed improvement, the clock frequencies have also increased exponentially, a corollary of Moore's law. The Moore's law depending upon the year and the clock speed ranges. It is the basic building block of the speed improvement stages. The year-wise 1970 and 1975, in 1980 and 1985 and 1990 and 1995 and 2000 and 2005. In the clock speed level, in 1971, 1975 10, in 1985 100, in 1990 1000, in 1995 10,000 and the 2005 above 10,000. Why more transistor per IC? The IC means integrated chip. And why faster computers? Why more transistor per IC? The smaller transistors, larger dies. Why faster computers? Why more transistors per IC? The first one is smaller transistor, larger dies. And why faster computers? Smaller, faster transistors, better micro architecture, and fewer gate delays per cycle. The scaling. The only constant in VLSI is constant change. Future size shrinks by 30% every 2 to 3 years. The transistors become cheaper, the transistors become faster, wires do not improve and may get worse. The scale factor S, typically S is equal to squared root of 2. The technology nodes. The scaling assumptions, what changes between technology nodes, constant field scaling, all dimensions x, y, z is equal to or greater than w, l, tox. The voltage VDD, the doping levels, the lateral scaling, only gate length L. Often done as a quick gate screen, S is equal to 1.05. The device scaling, consisting on length L and width W, gate oxide thickness and supply voltage and threshold voltage and substrate doping beta constant and resistance, gate capacitance, gate delay, clock frequency, dynamic power dissipation, chip area, power density and current density. The device scaling. The device scaling length is equal to the tabulation based on 1 by S and the width 1 by S per 1. The gate guide thickness 1 by S and 1. The supply voltage VDD 1 by S 1. The threshold voltage 1 by S and 1. The substrate doping S and 1. The current and resistance R and the gate capacitance and the gate delay. The clock frequency F and the dynamic dissipations and the chip area and the power density and the current density. The device scaling and the length and the width and the gate oxide thickness, especially in the supply voltage 1 by S1, threshold voltage 1 by S1, the supply substrate doping S1. The current is W minus 1 divided by L and 1 by Ts. The resistance or capacitance C and the gate delay and the clock frequency, dynamic power dissipation and the chip area, power density and the current density. The device scaling, the length L is equal to 1 by S and gate oxide thickness and threshold voltage level and substrate doping and resistance, the gate capacitance and the gate delay, dynamic power dissipation and the chip area and the power density and the current density. The device scaling of the this device in the length, width, gate oxide thickness and supply voltage and the substrate doping and current level and resistance beta of VDD minus VT whole squared 1 by S and S. The resistance value VDD divided by IDS 1 and 1 by S. The gate capacitance C WL divided by TX 1 by S and 1 by S. The gate delay, the clock frequency and the dynamic power dissipation and the chip area and the power density and the current density. The device scaling length, width, gate oxide thickness and supply voltage and it is the observations of the gate capacitance per micron is nearly independent of processes, but on resistance micron improves with the process. The gates get faster with the scaling. The dynamic power goes down with the scaling. Current density goes up with the scaling. And the velocity saturation makes lateral scaling unsustainable. For example, the gate capacitance is typically about 2 ff per micrometer. The F04 inverter delay in the TT corner for the process of future size is about 0.5 fps. Estimate the hand resistance of a unit 4 divided by 2 lambda transistors. The solution, the gate capacitance is typically about 2 ff per micrometer. The F04 inverter delay in the TT corner for a process of feature size is about 0.5 fps. The estimate on resistance of a unit 4 divided by 2 lambda transistor F04 is equal to 5 tau is equal to 15 RC. The RC is equal to 0.5 F divided by 15 is equal to F divided by 30 PS divided by nanometer. If W is equal to 2F, R is equal to 8.33 kilo ohm, unit resistance is roughly independent of F. Scaling assumptions. The wire thickness hold constant versus reduce in thickness, wire length local per scaled interconnect, global interconnect, die size scaled by DC is equal to 1.1. The interconnect scaling based on the width W, spacing S, thickness T, interlayer oxide height and wire resistance per unit length and fringing capacitance per unit length, and parallel plate capacitance per unit length, total wire capacitance per unit length, and unrepeated RC constant per unit length, and repeated wire RC delay per unit length, and crosstalk noise. The interconnect scaling: width 1 by S, spacing 1 by S, thickness 1 by S, and interlayer oxide height 1 by S, and wire resistance per unit length, and fringing capacitance per unit length, parallel plate capacitance per unit length, total wire capacitance per unit length, and unrepeated RC constant per unit length, repeated wire RC delay per unit length, and crosstalk noise. The interconnect scaling of the width level 1 by S, and spacing 1 by S, and interlayer oxide height 1 by S, and wire resistance per unit length 1 divided by Wt, the fringing capacitance per unit length, and parallel plate capacitance per unit length, and total wire capacitance per unit length, and unrepeated RC constant per unit length, and repeated wire RC delay per unit length. The interconnect scaling: width W, spacing, thickness, interlayer oxide height, and fringing capacitance per unit length, parallel plate capacitance per unit length, total wire capacitance per unit length, unrepeated RC constant per unit length, repeated wire RC delay per unit length. The interconnect scaling: width W, spacing T, thickness T, and interlayer oxide height, and wire resistance per unit length, and fringing capacitance per unit length, parallel plate capacitance per unit length, and total wire capacitance per unit length, and per unit repeated wire RC delay per unit length, and crosstalk noise. The width W, spacing, and the interlayer oxide height, and wire resistance per unit length, and fringing capacitance per unit length T divided by S 1 and S. The parallel plate capacitance per unit length W divided by B 1 1, total wire capacitance per unit length, and unrepeated RC constant per unit length, and repeated wire RC delay per unit length, and crosstalk noise. The interconnect scaling for influence of scaling of interconnect characteristics: sensitivity, reduced thickness, and constant thickness. The scaling parameters: width W 1 by S, and space S is equal to 1 by S, and thickness T, reduced thickness 1 by S, and constant thickness 1, interlayer oxide height 1 by S, and wire resistance per unit length, and the sensitivity 1 divided by Wt, and reduced thickness S squared, and constant thickness S, the fringing capacitance per unit length, and the sensitivity T by S, reduced thickness 1, constant thickness S, the parallel plate capacitance per unit length W divided by B 1 and 1, total wire capacitance per unit length CWF plus CWP 1 between 1 and S, unrepeated RC constant per unit length RWCW S squared between S and S squared, repeated wire RC delay per unit length, and crosstalk noise. And the interconnect scaling based on the influence of the scaling of the interconnect characteristics: sensitivity, and the width 1 by S, spacing 1 by S, interlayer oxide height so 1 by S, and the wire resistance per unit length 1 by Wt S squared, S, fringing capacitance per unit length T by S 1 and S, parallel plate capacitance per unit length, total wire capacitance per unit length, and unrepeated RC constant, and repeated wire RC delay per unit length, and crosstalk noise. The interconnect delay, the width W is equal to 1 by S, the spacing S is equal to 1 by S, and the interlayer oxide height 1 by S, the length is equal to 1 by S, unrepeated wire RC delay is equal to, and repeated wire delay. The interconnect delay, width, spacing thickness, interlayer oxide height, length, unrepeated wire RC delay, repeated wire delay, length, unrepeated wire RC delay, repeated wire delay. The interconnect delay, the observations, the capacitance per micron is remaining constant, about 0.2 ff per micrometer, roughly 1 divided by 10 of gate capacitance. Local wires are getting faster, not quite tracking transistor improvement, but not a major problem. Global wires are getting slower, no longer possible to cross chip in one cycle. The ITRS, the Semiconductor Industry Association forecast, the technology roadmap for semiconductors, the VDD in 2001, and the future size 130, and the 1.12 1.12 in 2004 1 to 1.2, 2007 0.7 to 1.1, 2010 0.6 to 1, 2013 0.5 to 0.9, 2016 0.4 to 0.9. Millions of resistors and transistors per die. In 2001 193, in 2004 385, in 2007 773, 2010 1564, 2013 3092, and 2016 6184. The wiring levels in 2001 8 to 10, in 2004 9 to 13, in 2007 10 to 14, 2010 10 to 14, in 2013 11 to 15, in 2016 11 to 15. Intermediate wire pitch nanometer 450 in 2001, 2004 275, in 2007 195, in 2010 135, in 2013 95, in 2016 65. The interconnect dielectric in 2001 3 to 3.6, in 2004 2.6 to 3.1, and 2007 2.3 to 2.7, in 2010 2.1, in 2013 1.9, in 2016 1.8. Input output signals in 2001 1024, in 2004 1024, in 2007 1024, in 2010 1280, in 2013 1408, in 2016 1472. In clock rate 2001 in 1684, in 2004 3990, 2007 6739, in 2010 11511, 2013 19348, and 2016 28751. In F04 delays per cycles, in 2001 13.7, in 2004 8.4, in 2007 190, in 2010 218, in 2013 251, 2016 288. The DRAM capacity of gigabits in 2001 0.5, 2004 1, 2007 4, 2010 8, in 2013 32, 2016 64. And the scaling implications, improved performance and improved cast, interconnect woes, power woes, productivity challenges, physical limits. The cost improvement in 2003 $0.01 bought you 1 lakh transistors Moore's law is still going strong, and the two diagrams are given below. It is based on the units and the data question. The interconnect was SIA made a gloomy forecast in 1997. Delay would reach minimum at 250 to 180 nanometer, then get worse because of wires. But it G means gate delay and the sum of delays, and the sum of delays Cu and low K, interconnect delay A and SiO2, interconnect delay Cu and low. Interconnect was SIA made a gloomy forecast in 1997. Delay would reach minimum at 250 to 180 nanometer, then get worse because of wires, but misleading scale global wires. The 100 kilo gate blocks OK. The gate delay, sum of delays, and interconnected delays. The reachable radius, we cannot send a signal across a large fast chip in one cycle anymore, but the microarchitect can plan around this just as off-chip memory latencies were tolerated. The dynamic power. The Intel VP Patrick Gelsinger, if scaling continues at present pace by 2005, high-speed processors would have power density of nuclear reactor by 2010, a rocket nozzle, and by 2015, surface of sun. Business as usual will not work in the future. Intel stock dropped 8% on the next day, but attention to power is increasing. The static power and the VDD decreases save dynamic power, product thin gate exits and short channels, no point in high value because of velocity saturation. VT must decrease to maintain device performance, but this causes exponential increase in off leakage, major future challenge. It is the statistical diagram for powers and Moore's law 3. The productivity, the transistor count is increasing faster than designer productivity, gates per week, bigger design teams, up to 500 for a high-end microprocessor. More expensive design cost, pressure to rise productivity, rely on synthesis, IPs, need for good engineering managers. The physical limits, will Moore's law run out of steam? Cannot build transistors smaller than an atom. Many reasons have been predicted for end of scaling, dynamic power, subthreshold leakage, tunneling, short channel effects, fabrication costs, electromigration, interconnect delay. Rumors of demise have been exaggerated. VLSI economics, selling price S total minus S total is equal to C total per 1 minus M. M is equal to profit margin. The C total means total cost, a non-recurring engineering cost, and a recurring cost and a fixed cost. NRE, engineering cost depends on size of design team, include benefits, training, computers, CAD tools. Digital front end $10K and analog front end $100K. Digital back end $1 and prototype manufacturing mask cost $500K and the 1M in 130 nanometer processes. The test fixtures and package tooling. Recurring costs. Fabrication, wafer cost, dice per wafer, yield, wafer cost $500, $3,000, dice per wafer, n is equal to pi r squared divided by a minus 2r divided by square root of a. Yield y is equal to e power minus ad. For small a, y is equal to 1, cost proportional to area. For large a, y stands to 0, cost increases exponentially. Packaging test. Fixed cost. Data sheets and application notes. Marketing and advertising. Yield analysis. Example. You want to start a company to build a wireless communication chip. How much venture capital must you raise? Because you are smarter than everyone else, you can get away with a small team in just 2 years. 7 digital designers, 3 analog designers, 5 support personnel. Solutions. The digital designers and analog designers and the support staff and fabrication. The digital designers based on salary, how much amount of salary you should be given, overhead, how many number of staffs overheaded, and a computer, what are the other than human resource, and the CAD tools, it is the simulation purposes, and total. The analog designers based on salary, in even overhead, computer, CAD tools, and total. The support staff based on salary, overhead, computer, and total. The fabrication based on back end tools, masks, total, and summary. The solutions of the following based on the digital designers, analog designers, support staff, and fabrication and summary. Digital designers salary, overhead, computer, CAD tools, and total. Analog designer salary, overhead, computer, CAD tools, total. Support staff based on salary, overhead, computer, and total. The fabrication based on back end tools, the last end of the tools, and the masks, total, and the summary. The solutions. The digital designers support staff and analog designers fabrication, and the summary. The digital designers 70k salary, 30k overhead, 10k computer, and 10k CAD tools. The total is equal to 120k into 7 is equal to 840k. The analog designers 100k salary and 30k overhead and 30k computer and 100k CAD tools and 240k and 720k. The support staff 45k salary, 20k overhead, 5k computer. 70k into 5 is equal to 350k. The fabrication, back end tools, masks, and total. The back end tools 1M and mask 1M and a total 2M per year. Summary 2 years at 3.91 M per year. 8M design and prototype. The cost breakdown. New chip design is fairly capital intensive. Maybe you can do it for less. It will be divided into salary, overhead, computer, entry tools, and back-end tools. The salary 26% in overall, the overhead 11% in the overall, computer 4% in overall, entry tools 9% in overall, back-end tools 25% in overall, fabrication 25% in overall.